Alright, so in today's video we're gonna check out different distance metric. So in the previous video we created the nearest neighbor kind of classifier, and we used some distance metric. So here we use the Euclidean distance. It's the one that most people are familiar with, but sometimes it's not the best distance depending on your problem set or your data. So we're gonna go through I think five different distance metric that you might come across, and honestly those are the most common one. After that you have some different distance metric with like a boolean data, integer data, but anyway, so we're gonna go through those five just to give you a breath, and we'll check out some visualization about what the distance surface look like. Right, so our first distance is the Euclidean distance. So it's the one that most people are familiar with. It's like a straight line between 2 points. So here, can I zoom in? Yes. So here you have point P and point Q, and basically you're trying to get D over here, distance PQ. So this is a straight line. There's no curvature in here. It's the shortest distance between 2 points. Here there's this simple formula: the difference in x in one dimension, and here this is the difference in the other dimension. You can have this in like 3 dimension or 4 dimension, but we have this formula. So this difference exponent 2 plus this difference exponent 2 give us this distance exponent 2. So how do you get the actual distance? Is you take the square root. So the formula is actually this square square root, yeah. So this is what we get, and this is what we get over here in 2 dimension, and in high dimension just chain them all up and you get this mess in 4 dimension. So if we were to code that in Python, let's say, it won't be too complicated. So the code for the Euclidean distance is the following. So you have as input a vector x1 and a vector x2, and you return just a scalar, which is like a number that represents this d. Here this can be like 2 dimension, 3 dimension, n dimension. So what we're doing is we're iterating over both vector, and we're taking each dimension one by one. So literally the scalar x1 and scalar x2. And then what we're doing is we're calculating the difference exponent 2 over here, and then we're creating an array of all of these differences. And what we do after that is the summation of all of these, and then we square that. And if you look at it, this is basically it. What we're doing is we're creating this, we're calculating all of these separately, right? And then we're creating this array of all of these, and then we're summing them up, and then we're squaring them. It's not the most efficient, but that works. So if we were to visualize that Euclidean distance, it will be pretty easy. It will be like a series of concentric circles, because if you have a point in space, and then you have a distance of 1, let's say, and you try to turn it around, you're gonna create a circle. Otherwise you cannot create a square, because this will elongate at some point. So it's going to be a circle. So let's check out the code that I'm doing for visualizing them. So the first thing I'm doing here is I'm generating a distance matrix. It doesn't matter too much what I'm doing here, but I'm creating like a grid, and then it's basically creating a grid and then taking the value of each of these points with the origin of this grid, which is in the middle of the whole thing. That's how I get my distance, and I'm going to use this function on each of my distance matrix. So the first one is Euclidean distance. So I'm doing this, generate matrix Euclidean distance. This is the only thing I need to give, and I get my x, y, and z matrix, and then I can use like matplotlib to make my contour plot. And they kind of look like this. So this is my origin, right? And I'm calculating the distance between this point and everything else. And you see I create a circle over there and another circle over there. And all of the circle are kind of the same size. Yeah, that's Euclidean distance is the most simple to reason about. All right, so the next one is Manhattan distance. So it's called also the block distance. It's a more squarey one, and let's take a look at Manhattan. So here we are. This is Manhattan. It's pretty. It's a square kind of city. It's kind of squarey. So we call it the Manhattan distance because if you were here on a taxi cab and you wanted to go over there, you have no choice but to go like this and then like that, and that's the shortest distance. But you couldn't go like this way because there literally are city blocks blocking you. So this distance kind of makes sense in different contexts, right? Where like cutting through a different dimension at the same time doesn't make sense. Yeah, that's basically it for this one. You could imagine like a Manhattan in multiple dimensions, so it's a 3-dimension where you could only go like in this dimension, and then up, like if you were in a 3D Manhattan, I guess. Yeah, so let's look at the formula. So here you have it. So it's the sum starting from I equal 1 till n, which is the number of dimension for this vector and then this other vector. And basically what you're doing is you're comparing each dimension. You're comparing each dimension one by one and just doing them a difference, and then taking the absolute value so that if one was bigger than the other, it doesn't matter. And then that's it. You're just moving like on a straight line in this dimension, and then doing plus for the straight line in the other dimension, and then plus in the straight line in the other dimension. So since there's no curvature here, it will look more blocky. So let's look at the code. So the code is kind of simple. Like if you got the Euclidean distance one, you're gonna get the Manhattan distance one. So you still have a vector here and another vector and a return distance scalar, basically. So we do the same trick as before. So we iterate over each dimension of these vector, and then we're doing like this one minus the other one, and then doing the absolute value. We get all the difference, right? And then we're summing them up. That's it. Well, let's look at the visualization now. So here's the visual for the Manhattan distance. So here it was the Euclidean distance. You can see the difference. It's more blocky than the other one. If we here you see at the distance 1.5, we got a kind of square around 0.0. So here, if we want to go from 0 to 1.5, it will literally take 1.5 because you're doing like difference between 0 and 1.5, and taking the absolute value of this. But what is interesting, if you take this part, let's say 0.75 comma minus 0.75, it will still take 1.5 because you're going to do 0.75 in one direction and then 0.75 in another direction, which will sum up to 1.5. While in the Euclidean distance, you can just cut straight through. Yeah, it's pretty intuitive, and it's used when you can't. There's no physical way of cutting through stuff. Right, so the next distance that we're going to look at is Chebyshev distance, which is kind of like the maximum, call it the maximum distance metric. So basically what it is that you're looking at the difference again in each of your axes, and you're just figuring out like which one is the maximum absolute difference. And then there's this example. Can I take a look at? Yeah, whatever you can see here. So if you have a chessboard, you can have like 2 dimension, right? So because it's kind of like a map. The Chebyshev distance from here to everywhere else is those numbers, because like here what it is really is the king can move diagonally and at 1. So the distance between here and here and here and here is the same, because if you look at the difference between, let's say, 0, 0 and 0 minus 1, that's 1. And then if you look at the difference between 0, 0 and minus 1 is also 1, right? The maximum difference, because you have 1 in this direction and 1 in the other. So you take the maximum of this and that's gonna give you 1. It took me a while to catch this example, but it kind of makes sense if you think about just taking the difference, the absolute difference in all dimension, and then just taking the maximum that you found. So if we take a look at the code, it's pretty intuitive. So again, our same old trick of doing like the vector thing, the list comprehension thing, but here we're just taking the difference, and then we have an area of difference, and then we're just taking the maximum in this array. That's it. So if we visualize this, it will kind of be the same thing as before, but kind of more squarey, I guess, less of a lozenge. Yeah, that's it. Because like if you think about it, here we're at 2.4. No matter in this direction, right? If we're over here at minus 2.4 and like minus 2.4 in x and y, that will still be 2.4, right? If we're at 2.4 over here and 0 in the x-axis, that will still be 2.4. So it's kind of a rectangular, well, actually a square matrix around the origin. Here it's more of a lozenge, because you could do like tack. So those two are kind of related, but yeah, just think about the maximum. Right, so the next one we're gonna check is the Minkowski distance. So this one kind of a generalization of two that we saw before. Yeah, so generalization of the Euclidean distance and the Manhattan distance is because we're controlling the exponent that we're using. So if we take a look at this, that will be, this is the formula, that's it. So you remember this sum over here, if you remove this and that, that's literally the Manhattan distance, right? If you put a 2 over here, that's literally the Euclidean distance, because you're doing exponent 2 over here and square root, but then you can do exponent 3, exponent 4, you can even do exponent 0.5. So kind of look like that's kind of cool, and then at infinity will just be like a big huge square, and here will be a bit rounded if you go 2 to the exponent 2. If you put 0, you're gonna get that, and if you put 2, you're gonna get that. So Euclidean, Manhattan, so this is kind of a generalization. So let's take a look at the code. So once again, not too difficult. We have this vector, this other vector, and then p, which is our order of the distance to be calculated. And if it's the same thing as the Euclidean, except that we're gonna have there's gonna be a power over here, right? And then here we're gonna do times 1 divided by p, and we're summing the difference. But it's the same kind of trick that we're using. So let's take a look at how it behaves with different p. Okay, so this is Minkowski distance at 1, right? So we get the Manhattan distance. At 2 we get the Euclidean distance, and then at 3 we kind of get like some squarey kind of thing, and then it gets more and more squarey. Yeah, my plot is a bit messed up here, but yeah, this just gets squarey, but like more squarey. Yeah, good. So let's take a look at the last one. Last distance that we're gonna check is the Mahalanobis distance that was figured out by this fellow over there. So the vanilla version, what you have is a vector here with many different dimensions, and the many different dimensions have behaved differently. They're not like the same. So you have different mean for each of the dimension, and you have a covariance matrix for how each dimension vary together, right? And if you have those three components, then you can calculate the Mahalanobis distance. But sometimes you don't have this other mean. So if you have two different vectors and you suspect that they have the same distribution, and you happen to have the covariance matrix of that distribution, or you kind of modelize it, you can use this version of the Mahalanobis distance to calculate the distance between the 2 points in multidimensional space. And it's also called the generalized squared interpoint distance. Yeah, that's it. So that's the formula. So you have this vector minus this other vector transpose times the inverse of the covariance times the difference again squared. Let's take a look at what is actually a covariance matrix. So that's kind of like, this is a covariance matrix that represents this, and what it is you know, the kind of Gaussian distribution that you can have. Like sometimes this is how you say that this feature is distributed like this, but if you have this plot, you can't say that anymore because there's 2 dimensions. So how does it vary, like across this and across that? So you need something to kind of represent this, and the covariance matrix give you that information. That's it. So it's a cool, kind of bit complicated, but a cool one. But yeah, you kind of need to have some prior knowledge about what the covariance matrix look like, and it's a strong assumption that the 2 random vector have this exact same distribution. Yeah, maybe they are, but like you just have to take this as an assumption. So let's look at how we implement this. All right, so here's the code. So it's pretty simple. What we're doing here is we're calculating the difference between x1 and x2, which are our 2 vectors. Here, this is the covariance matrix, and basically we're taking the inverse of it because that's what the formula requires, and we're doing a dot product between those 2, and then a dot product between the result of this dot product and the delta, and then we're squaring everything else. Yeah, I used NumPy because I didn't want to reinvent the dot product. So let's take a look at what kind of visual do we get. So here, this is the Mahalanobis distance. I used the lambda function just to be able to give my stuff. And if you look at my stuff over here, this is that covariance matrix over here. So kind of a Gaussian that is like 2 Gaussian together, one thicker than the other. Yeah, and we get that kind of distance. How do you interpret this? If you go from this point to this point, or this point to this point, it's the same. Yeah, it's a bit harder to interpret. I'm not sure how to interpret this one, honestly. Yeah, it's a bit difficult. But yeah, for sure. Like if you know the covariance, you know that those 2 are the 2 vector are coming from the same distribution. It's kind of stochastic. It's a better kind of a distance metric to use. And actually, like I think if you're using the identity, I'm pretty sure we can get back to if we're using 0.0. I think we can get back to Euclidean distance. Yeah, actually, if you use the identity kind of matrix, so 1 0 1 0 0 1, you're actually gonna get back the Euclidean distance. So here you're assuming that the covariance is, yeah, here you're assuming that they're independent. So if I kind of look at it properly, So this vector with this other vector, so this dimension with this other dimension, they covary perfectly, and then this dimension with this other dimension, they do not covary. So you're assuming that they're independent. Yeah, I guess. So this one I have a bit more difficulty to get a grasp on, but I believe that if you know the how the covary, you know the distribution, and you characterize this very well, then you get a more accurate kind of a distance metric. So that's it. I hope that you've enjoyed this video. If you have any comment, or if I messed something up, don't hesitate to leave it in the comment section. And like always, have a great week.